Morning, everyone.
Yep, go for it. Have fun.
Right. My name is Andrew. I'm Andrew Glass. I work at Microsoft, and in my spare time, I collaborate with this group of folks on the what do we call CLDR Keyboard Working Group. And so, yeah, I just want to certainly shout out. Craig is in the room. We had a talk from Tex yesterday, and Naved was here yesterday. And so there's amazing stuff that's been happening, mostly from the volunteers, and I get to represent their work today. The mission of this working group is simply to try to connect primarily digitally disadvantaged language groups to technology platforms so that we can close that gap between when a language gets encoded and when you can use it on a phone or a computer system. So our goal is to put Unicode and CLDR in the middle here and make sure that language communities can talk to CLDR and submit their keyboards. And on the other side, technology companies have a place where they can come to and reliably get high quality keyboards. And keyboards for languages which getting resourcing, getting engineering teams to understand how to create a Go and Kama keyboard is a tall ask, and so we want to solve that gap. We've been around for about 5 years, working on a roadmap, which I'll be sharing in a moment, and we meet monthly. Anybody is welcome. We're about to change phases. And so, so the work is going to shift up a little bit. Sometimes we meet every 2 weeks when we've got a technical topic we want to solve. But it's and we meet online. The team is very distributed around the world. We have folks in, Mark Durden is in Germany, Stephen Loomis is in Texas, Craig is here, I'm in Seattle. We have another partner, Jan Kuchera, who is in the north of England. And so we have other partners. Ross is in Perth, and we've had participants from Cambodia as well at different times. So scheduling the meeting in a time zone at a time that works for everybody is one of our biggest challenges. So my personal sort of Unicode philosophy is, and this is important for understanding, where does keyboards fit into the situation? Really, Unicode is about the computer layer, the storing, transmitting, and computing with language data. And it does so in the ones and zeros that we all spend many hours discussing, what are the code points involved. One of the things that I find is challenging is that people get very attached to the code chart, and they get very attached to which elements are in the code charts, what gets an atomic code and what doesn't. And I see this as really, those are all decisions about the computing architecture at the Unicode level. Ideally, the font and the font stack translates the ones and zeros of Unicode into something on the screen that the users of the system recognize as correct orthography for their language. And so conversely, the keyboard system is responsible for taking something that makes sense to the user and converting it into the ones and zeros that the computer is going to store. So in a perfect world, language communities would have very little concern about some of the technical decisions that we make at the encoding level, because they would be insulated from it. What they care about is that the text displays the way they would like it to display, and that they can enter it the way they would like it to enter it. And then, of course, they want to be able to sort it the way they would like to sort it. And so those are the most important things to me about some of the encoding decisions we have to make. Now, for historically, and for good reasons, Unicode has put a lot of focus on the font side of this. I'd say the majority of the focus has been on the font side because that is the most immediately pressing problem. And there's a lot of complexity and a lot of effort that has gone into fine-tuning our font stacks and our display stacks in order to create, to really bring forward the orthographic authenticity of the text that we display. Keyboards, on the other hand, have certainly received some attention. But if you sort of look at the span of 30 years now of Unicode, or 30 plus years of Unicode, keyboards have not taken the technology involved to the same level as the font stack. And as a result, there have been some challenges in some of the encoding models where the user community is typing, and they're typing with what is a simple typewriter effect. And so then they have to understand the encoding model in order to get out the display that they want. And so those two things, the fonts and the keyboards, are not in balance. So part of our goal, working closely with SIL and Mark and Stephen, in creating this new push to get the Keyboard Working Group to support language communities getting their keyboards into Unicode, is especially around this angle of how do we really make sure that the keyboard data that we collect represents the orthographic needs of language communities, and how do we make it really easy for them to enter their languages? And that's where it becomes especially difficult for major companies who are providing these systems in most cases to have the language expertise and the time and the resources to devote to making all of those decisions about what language to support and how to support them. All right, so here's my tube map. People say road map, but I prefer this model. It's tube map. It's kind of purple, so Metropolitan line, if you are familiar with London. So this is where we are, where we have been, and where we're going. So we introduced the new specification, which allows us to capture all of this information about the keyboard requirements. Yeah.
2004?
See, I'm living in the past. Thank you. 2024. Yeah. Yeah. Can I edit that live? I can't edit that live. Thank you. 2024. We released version 3 of the keyboard specification. The keyboard specification has been around for a while. I'm not sure exactly how long. I was involved in version 2, which moved the needle. And then version 3 was really when we got critical mass in terms of the capabilities and the working group that came around to support it. So this 2023 was soon followed by 2024, April 2024, May 2024, the reference implementation in SIL's Keyman Developer, which you were mentioning earlier. Love that program, and we'll be taking a look at that in a moment. Then we developed some intake procedures. So our goal is to collect information about keyboards from, open to all sources, evaluate them on the model of the script encoding working group, and then propose them to CLDR to ingest into Unicode so that they become available to major platforms, applications to consume. So we developed these intake procedures in 2025. Oh, good, I got the 20s in this time. And so that is hot off the press just last month. And this past week, we submitted our first set of keyboards to the repository to get it kickstarted. The 4 that we submitted, we'll take a look at in a moment. But these were a keyboard for Gandhari language, a keyboard for Sanskrit in phonetic input order, a keyboard for classical Tibetan, and a keyboard for Egyptian hieroglyphs. Right, so next steps. We believe that we need design guidelines in order to help language communities and those who are supporting language communities through the encoding process to help them understand the capabilities of keyboards and what are some good choices to make. In parallel to this, as we heard from Tex yesterday, there are some efforts to use AI to generate keyboards, both at University of Limerick and also at Silicon. There was an intern project this summer to try to leverage the power of AI in order to understand and develop those keyboards. Right, and then we get into this loop at the end of the roadmap where we are sourcing keyboards from various sources. Through our partners, Silicon and Limerick, ideally, the script encoding working group, in addition to expecting encoding proposers to provide a font, it would then be a light lift for them to also come with a keyboard. And having the keyboard and the font together actually improves the quality of the encoding because you understand what you see at each step of the user's journey in terms of inputting a language. So all of that will build up in CLDR a repository of keyboards, which we hope then to attract the attention of Microsoft, Apple, Google, Amazon, and any of the platforms who are providing keyboards as a service to their customers. And it would also be something that smaller apps or language communities could sideload as well and complement the work of SIL on the Keyman keyboard repository. So the idea is that then we get this positive cycle of reinforcement. When platforms have adopted LDML version 3 as an input format for keyboard data, then that creates a motivation for language communities to identify, oh, how do I create a keyboard for today's world? Well, you do it in LDML3 because that is the format that is supported by technology platforms. But in order to get them to support LDML v3, we need to have critical mass in the keyboards. So that is the stage that we're at. We're just trying to start this virtuous cycle of developing keyboards and using them. And then it flows into the CLDR model. One of the attractions for a tech platform to get their keyboards this way is that they are not on the hook for, one, engineering the keyboard in the first place, and two, addressing the data bugs in the keyboard, because that becomes an issue for CLDR and the language communities to experience the keyboard, to use it, to file bugs, and to fix bugs through the CLDR process. Right. So with that, I want to do an initial demo with Keyman Developer. Hands up if you've heard of Keyman Developer. Okay, a few. It's actually very easy. So it is a fantastic program. I'm extremely grateful to SIL for taking the lead in running this with to get LDML3 off the ground. So what I'd like to do, this is on the correct screen. I'm going to start a new project. So LDML is a keyboard project type. So I'm going to open that. I have to give it a name, so we'll call it Unicode Technical Workshop 2025. I didn't miss the 20s this time. A test. And then I think I have to put something in here, so we'll choose a PGD, and we'll call it Latin. Okay, something like that. Okay. Okay, now that's on the other screen. All right, so it opens the keyboard And we can look into this new keyboard, and conveniently, it is already populated with a functional keyboard, which is great. We have in the part of the goal of the V3 specification was to make sure that we could define keyboards for hardware keyboard layouts and software keyboard layouts in the same data file, in the same XML. So the anatomy of this XML file is that we have a set of keys defined, which we affectionately call the key bag. We have a section of layers, which defines which keys go where. And we have, not here, we can put in a section of transforms, and we'll see that in a moment. But let's just get started with creating something. If I build this, I can build it already. And then I can open the test. And that's super small, but I can type. And so this is taking the input from this keyboard. So if I take a layer, such as this one, and I introduce it as a new layer, there will be a graphical user editor for keyboards. That's planned for at some point, but in the meantime, we have XML. And so what I've done is I've added a modifier here to Alt-R. So the Alt Grav key, which is your right Alt key on the keyboard, that is now this layer. And if I were to say this has inherited all of the key identifiers as the base layer, but if I create a new identifier, Alt-A, and then I come up here, in the keys section, we're importing all of the standard keys for the US keyboard. So I need to add a key, and I will give this an ID, which is the same one I just added down here as Alt-A. So that's what this this layer identifier does is it knows what Alt-R is, and it will look up this key ID, and it will come here, and it will ask what the output should be. And so I can, put whatever output I want in here, but let's do a Unicode value. In fact, let's just do the A, and we'll do 0301, something like that. So now if I build this, okay. Now I come down here, and I'm going to press the Alt-Jar key, so I need a camera right here. And the A key, it has output A plus the combining diacritic 301. So it was as easy as that. You just, one line of HTML, what you want your identifier to be, what you want your output to be. Obviously, this is just the beginning. We can be a lot more powerful. And so that's what I'd like to do to walk us through in the next sections. But before we get to that, okay, so you've written your keyboard in LDML, and what do you do with it? So you create your keyboard, and you open a Jira ticket, which is the issue tracking system that Unicode uses, and you say, I need this new keyboard. And then you create a commit for that new keyboard, and you open a pull request. Then the keyboard working group will review the ticket and the pull request, and we will possibly iterate with the author on exactly the details of the keyboard. And then when the time comes, we will recommend the keyboard to the CLDR technical committee for inclusion in the next version of the standard. Now, because of the stability concerns around CLDR and everything that we're offering to platforms, we want these keyboards to be stable, but we recognize that particularly when you're developing something like a keyboard for use in a language community that may not be have access to the latest updates every month, it's very important to allow a period of time where you are open to taking changes. So we think of changes as two types for keyboards. There are destructive changes, where you decided to move a key from one place to another, or replace what key was input by a particular keystroke. And so we will allow those kind of changes while the keyboard is in a provisional state, in a contributed state. And we would keep it in that state for, maybe a year. We'll see. We're trying to feel our way through this process as we go. But then after that, the keyboard would be stable, and that would give a signal to platforms that this is something that you could depend on. And then we would not allow destructive changes. But if you wanted to extend, say, your community adds a currency symbol, and so that needs a place on the keyboard. And there was a free spot, so you put the currency symbol in, and then you submit the keyboard. And that kind of change is fine, because nothing broke. All right. So this is looking at the commit. It's on GitHub. Anybody can go there. You can take down, clone the repository. You can make your LDML edits. You can put up a pull request. So this is the pull request for the latest keyboards that we submitted. And so I'd like to look at those in a bit more detail, and in the process, kind of elucidate some of the capabilities of this keyboard system. It's sort of an evolution of Keyman in a way, but the format was also designed to be easy to import for platforms who are providing keyboards. So at Microsoft, we have keyboard data for about 200 keyboards, and maintaining that is hard. We'd love it to be easier, and so this is the path forward for that. So here is a page of Tibetan script in classical Tibetan. And let's see if we can type this. Actually, I'm going to do it this way. Let's do it in Keyman Developer. Take this off here. And we shall build this. All right, so that built successfully. All right, so the first thing that we see on the top left here is a birga. It's a head mark. Sorry, birga is the Mongolian word. They have the same looking mark. And where did I put this on the keyboard? I put it on the tilde key. So I'm going to press the tilde key, and that output the first half of our head mark. Okay, so far so good. And then I'm going to press exactly the same key again. So it was easy for me as a user to get the right thing to happen, because obviously I didn't want two of the opening head marks. But unlike Arabic, where we do sort of the word positional font change, this was an atomic character change. And so atomic character changes happen at the input stage as I'm typing. And so the context here was we had 0F04, and we received another 0F04 from the key press. And so we knew, because of the logic that's encoded in the keyboard, to not output the second 0F04. We now output 0F05. Is that clear? Great. So let's look at exactly where that happens in the 0, 0, 4. Here it is. So when we have 0F04 followed by 0F04, then what we output is 0F04 followed by 0F05. And then if we have to have a second rule, If we already have a 0F05 followed by a 0F04, then we need 2 of the 5s. So if I press the tilde again, then I get the same thing. So I can extend that as much as I want. All right, so far so good. I'm going to press the pipe symbol, the backslash, and that gives me this she character in Tibetan. And now I'm going to press space. Now, space has also got special behavior, because if I did, say, a letter, such as ka, and then I press space, space outputs this dot, this tooth called sek. But when I have the pipe, the she, and then I press space, it knows that I don't want the sek in this case. And so we have another substitution rule that says, look at the previous context and choose the correct form for the space character. So I can do that. I get another one of those. And then I can type, this is a ra, this T-shaped thing on top. I can take the G, and I can type the Y, and I can put another tooth. So if I typed R space G space Y space, that would have given you the atomic values, the full form of each of those letters. But while we are typing, we are reanalyzing the sequence deterministically and adjusting what the user intent is at every stage of the key press. So if you're a Tibetan user, that will make complete perfect sense, and it will also match your expectations, because if you're thinking about a phonetic keyboard, that's what you would expect to happen. Because if you're transliterating into Latin letters, the key presses are what you would have transliterated into. So this is special. So what happened here was I pressed the G. Tibetan is one of these it's a modification of an Indian Brahmic writing systems that have an inherent vowel, but the behavior of inherent vowel in Tibetan is quite special. We don't need to spend time on that, but the point is that when you're trying to anticipate where does when to stack and when to split, the phonetic transcription has to inform the user, has to inform the system where this A goes, but the A doesn't exist. So if I type GR, then I get gra. But if I type GAR, then I have split. This thing in red down on the sort of the Unicode line that you can see, that is a marker. So that is a hidden symbol in the input buffer. It doesn't get transferred into the text control. So it only exists in the input buffer. And what it does is it informs the keyboard, it allows the keyboard to retain state that an A was pressed, but I didn't take an action in the edit buffer. And so it can tell the difference between the A as the inherent vowel, which had no impact on the way that the text was stored, and if A was not pressed. So the difference between GR is that, and GR, I'll give you a space, GAR is that. All right, so then we can do yeah, gar, do. All right, that's all the Tibetan we're going to type right now. But you can see how this works and how it's rethinking the input process as you're typing. Let's look at another couple of these. But we will now switch to trying to do this in Word so that you can see a cleaner version of this without without these red marks. So this is a Sanskrit text, and I originally wrote this keyboard about 20 years ago using Keyman for the benefit of scholars studying Sanskrit. So this is, there are many different ways of typing Devanagari, and this one has been designed to support the way that sort of Western scholars of Sanskrit think about Sanskrit. So I will first transliterate this into English. Thank you for the initial cap. Hello. Oops, I didn't have the keyboard with the, okay. There's a long vowel. Imagine that that's a long vowel. I don't have the correct keyboard for typing English. That's my problem. All right, so what I'm going to effectively do, I will use uppercase. So Sanskrit scholars would expect that to be a long A with a line above it, and this one as well. So let's do, so there is A. I'm typing just the A on the keyboard. I'm pressing the T. This is the classic shape of T with the halant. So this is the vowel canceller. So ta includes the vowel. If I put that foot on it, that's just T by itself without the vowel. That allows me to press, if I press A, it will take the foot off. If I pressed D, it would make a conjunct. But if I press H, it's going to turn it into something else. Because when we transcribe into Latin letters, we treat it as a digraph. But it isn't a digraph in Devanagari. They have more T's and D's than we have in English. And so in order to make it easy to type, it gets transcribed as TH. And therefore, as a user, you're thinking TH. And we know that we don't want to give you T followed by H, because that would be something else. But since T followed by H doesn't actually exist, or doesn't occur, we can know to give you the user this thing instead, which is ta. So we're leveraging a lot this ability to see what the context is and adapt the context. 5 minutes, right. Let us go to, oh, I'll finish typing. Right. So just type N-A-L-O-P-A. So again, this sort of, if I typed A by itself, it's that. And I type P, it takes that off. If I type O by itself, it's that. But if I type O in that context, it's that. We're on the top line. Okay. So that's this top line. And yesterday, we heard from Kartik about the differences in Devanagari between these, I guess these are the southern forms, and no, the other way around, and these forms. So that's a font level distinction. The font that I have happens to use that style that looks more like a 3, and then there's the kind of sun rays version in the printed version that I got this from. All right, so that's how Devanagari works. Let us go to, I want to do, let's see if we can get Gandhari to work. I'm not going to type this because it's a little tricky to see. What I want to do is actually give a different example from Gandhari and how the numbers work. So that's the number 1 in Gandhari, in Kharosthi script. That's 2, that's 3, and that's 4. In Kharosthi, they used an additive multiplicative system. So they only have symbols up to 4, and then they repeat at 5. So that's 4, 1, which is 5, and that's 6, and that's 7. So I'm just pressing the digits on the keyboard. And that's 8, which is 2 4s. So now you can guess what 9 is. So that's 9. Right. So we get another symbol from them for 10. So that's 10. So if I type 1, they didn't have a 0. 0 came a few hundred years later. And that's 1 followed by 0, which is 10. That makes sense to me. It's not authentic to the writing system, but it's easier to type. So if I type 20, it's that. If I type 30, it's 20, then 10. And if I type 100, it's that. And if I type 1,000, it's that. So if I type, let's say 50, let's type 500. That's 5, that's 4, 1. I turned it into 50, which is 20, 20, 10. And I just pressed 5 and then 0. And then I press another 0 to make it 500. And now that's 4, 1, which is 5, times 100, which is 500. And then I can press 0 again, and I get 5,000. So we're thinking through, how is the typist going to think about this number, and what is going to be the most intuitive way for them to input? And so that makes it life easier. Because typing 4, 4, 1, no thank you. All right, let's go to our final demo. My favorite version of Peter Rabbit is written in hieroglyphs. You can get this at the British Museum. Let's take a sample that looks like this. So the thing about keyboards, when you deal with 1 minute, when you deal with displaying fonts, it's very important to have, really ideally, one graphic outcome for one encoding string. But when you deal with keyboards, it is perfectly fine to have multiple different ways of typing the same thing. So let's just do the first, different language. Egyptian, okay, E34. So is that big enough? A little bit bigger, and okay. And do I have the right font? No. Egyptian text. Okay. So this font is available, and this keyboard is now available. So, so we typed E34, which gives us the rabbit. And then I type VJ to indicate that I want a vertical joiner. And that's going to be that. And then I'm going to type the water symbol. So I could write N, what is it, N35 for water. But I also know that the phonetic symbol for water in Egyptian is N. And so if I just type N, I also get water. So I can use the system that makes sense to me. Then I can type, is it P? Yes. And then W, and then S. And then this one on top is an animal part. And animal parts start somewhere like F37, but that's not it. So then I want to step through all of the F characters. So I'm cycling through these Fs in order to try to find what was this character that I'm looking for. Because I've forgotten. One of these coming up soon. Entrails, there it is. Okay, so this one. Now, if I want to back convert, I've got a rule on the keyboard that does that. I can turn it back into, what was that character? It was F32. So now I can do F32 and I'm done. So then it's vertical joiner and D36. So I think we're out of time, but that's how you type. Lots of different ways of inputting one Unicode outcome. Try to be very authentic to what the way the user thinks about the language that they're typing. And fortunately, Keyman Developer and LDML3 will give us that. So please bring your keyboards and we will add them to CLDR and we will add them to our major platforms. Thank you.